Okay, the topic we're looking at here is work, energy, and power. And if you go through the video series on work, energy, and power, there are an immense amount of topics that need to be covered. So you will come across topics like defining work, components of work and force, kinetic and potential energy, mechanical energy, where we will look at conservation of energy, the work energy theorem, concepts of power, and so on. So as the series goes through, you will cover these topics, and there are certain topics that we look at, or certain videos in the series that you watch, that require you to have a resource. If you want that resource, you're more than welcome to send me an email directly, and I will send that resource to you. So the first thing is defining work. We say that when a force acts on an object to cause the object to be displaced, then we say that work is done on the object. So when I look at the definition, it says that work is defined as the product of force and displacement. Covered by an object in the direction of the force. So when I look at that description, what are the four factors? So the four factors involved with work. So what we need to make sure that we have is we have some sort of force. And that force could be a push or any kind of pull, or an engine force would also be considered a force. The second thing is there needs to be displacement. That means the object must have some sort of motion that it goes through. The third thing is a cause. So what effect takes place? And the fourth thing is direction. So if I look at it, we say that in order for force to qualify as having done work on an object, there must be a displacement, and the force must cause that displacement. All right. Now, if the force causes that displacement, it means that the direction of the displacement must be in the same direction as the force. And that is how we can say that work is done. So when we're looking at the concept of work, we also look at the concept of energy. We say that when work is done, energy is transferred. Now, the energy we're referring to is mechanical energy. That mechanical energy can be added to the system or removed. Now, in terms of energy, there are different types of energy. We have what we call gravitational potential energy, which we're going to call EP, which has a formula mass times gravitational acceleration times height. And that is called the energy due to position. And usually position above the ground. So that's one type of energy that we look at. Another type of energy we look at is kinetic energy. Kinetic energy, which is EK, is the energy of motion. And the formula for that one is a half mass times velocity squared. So if I am talking about work being done, there must be some sort of energy transfer. We will look at mechanical energy at a later stage and how it is added or removed from the system. One important thing that we must realize is that energy cannot be consumed if work is not done. So this refers to normal energy consumption. If I'm sitting at my desk and I'm writing, I'm consuming energy, but I cannot say that work is being done in terms of the conceptual idea of work in the physics context. If I am, for example, doing yoga, I'm consuming energy physically, but if I don't have a force, I don't have displacement, I don't have a cause, I don't move in a certain direction, it means I cannot say that from a physics context or physics point of view, I cannot say that work is being done. So energy cannot be consumed if work is not done. And without energy consumption, no work is done. So you need them to work hand in hand. You will need to know how to calculate the work done on an object by a force, meaning if positive or negative work is done on the object. So the formula they give us here for work done is W is equal to F delta X. So the W over here, that stands for work done, and it's going to be measured in joules, and the unit of measurement is a capital letter J. We then have F. F is the force, and when we say force, we mean net force in newtons. And then we have delta X here, which is your displacement in meters. One thing that we must understand here is that in terms of energy, is that when network is done on an object, so if there's a total amount of work that's done on an object, the kinetic energy of that object will change. Now, when we look at work done is a scalar quantity. Because it is a scalar quantity, please understand that you can have negative answers. You can have negative joules. So when I have a negative value, I have what we call negative work done, and that is energy that is lost. I don't mean lost in the sense that it's gone. What we mean by energy loss is that it is dissipated to the surroundings as heat or light. If I have positive work, then a positive value, positive work done. And here we have an energy gained. Again, gained not in the proverbial sense that we're going to actually collect energy. Because there are going to be changes in the kinetic energy, we will look at how the energy is affected in these calculations. Now, something that is very, very important is when we look at this formula, the force that we use. The force has to be a net force that is acting on the object. So that is your resultant force, F resultant, which is your sum of your forces. So if you have a situation where you have components of forces like Fg perpendicular, Fg parallel, those forces must all be considered before substitution. My recommendation is that you work out the net force either using F net equals F1 plus F2 plus F3. Just remember here that you need to put signs into the formula if it is in the opposite direction of motion. The reason for that is because you want it to be a negative value, and you don't want it to affect, especially if it's a negative value, it's moving in the opposite direction of motion. Or you can use forwards minus backwards. We're not actually looking at the forwards minus backwards or how you got your F net. Just make sure that you've got your F net. When it comes to the direction, and you can use any kind of direction. You can use cardinal points. You can use left, right, up, down if you wanted. Whatever the case is. We say that when a force is applied on an object and it displaces. So if you apply force and it displaces that object, the displacement must be in the direction of the force. So if you push an object east, then it must move towards the east. If you push an object south, then that object must move towards the south. Your direction of your force and the direction of the displacement must be exactly the same. Now, if you had to push east and the object moves north or south or west, then we say that work is not done. In that case, if that's what happens, you need to actually check what forces are acting on the object. Have you used the net force? Is it the correct net force? But those two things, the force and the direction of the displacement, must be in the exact same direction. They must share the same direction. All right, in this first example, it says a force of 20 newtons is applied to a block of wood which has a mass of 3 kilograms. The block is displaced 22 meters. Calculate the work done. So they've given us an image here, and I can see from the image we have a block that is being pushed by 20 newtons of force, and it moves 22 meters. Now, in this case, we say, if I check my direction of my force, that is going east, and the displacement is to this point, which is also east. Already I can see that I can do the calculation. So W is equal to F times delta X. The force here is 20 and the delta X is 22. So the work done here on this object is 440 joules. Now, if we just have a look here, if I said work is force times displacement, and I said 20 newtons multiplied by 22 meters, I just want you guys to see the unit of measurement. We'll get 400 Newton meters. So it's another unit for work done. So we can say work done can be measured in joules with a capital letter J, or in what we call Newton meters, which is capital N lowercase m. So 1 joule would be equal to 1 Newton meter. So that's just another unit for work done. Okay, for the next example, it says a 13 kilogram mass accelerates at 3 meters per second squared and covers a horizontal distance of 41 meters. They want the work done by the mass. Now, if I look at my formula, we've got W is equal to F delta X. Now, I need to look for the work done. I've got the delta X, which is 41 meters, but I don't have the force. What I do have is the mass, which is 13 kilograms, and I've got the acceleration, which is 3 meters per second squared. Hopefully you're looking at this information and you can recognize that I can find the force. So the first thing you want to do is you want to find the force using mass and acceleration, and that gives us F net equals ma, which comes from Newton's second law. So you've got 13 multiplied by 3, and that gives you an F net of 39 newtons in the direction of motion. All right, once you've got that, you can go W is equal to F delta X, and that will be 39 multiplied by 41, and that should give you the work done as 1,599 joules. And because it's a vector quantity, there's no direction added to that. So you must also be aware that in this section, we will have Newton's laws coming in. Because we've got concepts like acceleration, and because we're going to have changes in velocity, we must be aware that Newton 2 and your equations of motion can also be brought into this section. At this point, what's going to start happening is that you can have a lot of your sections in physics starting to combine with each other. By the time you get to the end of grade 12, you will realize that physics is one just giant topic, and chemistry is one giant topic, with each of the topics that we cover being subtopics of that general topic called physics. So you need to get used to the idea of other topics being tested within a different topic. Now, one of the next things we look at is when is work done or not done. So if I look at the images that are below here, it shows 3 different scenarios, and we're just going to talk a little bit about whether work is being done or work is not done. So if I'm looking at the first one, it says, you can see the little character over there is lifting up weights, and what we can see that of the image, he looks like he's really struggling. So we know that he's exerting a force that is upwards, but we can also see that there's no distance moved. Now, because there is no displacement, we must say that work is not done. Now, this is only in the context of this topic. Yes, if you were at the gym and you were doing something, an activity like this, you would be consuming energy. But in the concept of physics, we say that work is not being done. If I look at the second image, we've got a person here and they're pushing a stationary wall and it looks like a lot of effort that's going into it. So there's a force that's being exerted to the right, but that wall is not moving. And because there is no displacement, we can say that work is not done. So again, no displacement, no work being done. If you were carrying your backpack and you were going to school, the fact that you're carrying your backpack means that there is a force that is exerted upwards in your backpack. However, if you notice here, the distance that you're moving is perpendicular to the force. So what's kind of happening here is that the force that is being applied is going this way, but the displacement is going in a totally different direction. So here we can say that no work is done because the direction of the force and the displacement is not the same. And they have to be the same in order for us to have work being done. So if I look at, this is a similar example, if I look at this waiter who's carrying this tray. Now what we can see is that the force that is being applied is from the arm to the tray. That is the force. So the force is an upward force. What we can also see is that the direction that this person is moving in is to the left. Now what we can see, like in the situation with the backpack, we can see that there is a force. Okay. Also, there is displacement. Automatically, our brain say then work is being done. Problem is, the force is the waiter pushing upwards. And the displacement is the tray. So upwards on the tray. And the tray is moving horizontally. That means that the force, and this is where the cause comes in, the force does not cause, and this is why I need a cause, the displacement. And because the force doesn't cause the displacement, it means that work is not done. Now, I can say that in words, but if I think about it like this, and if I had to actually look at my formula, and my formula is, so we can make a rule here that says that if I'm looking at the waiter situation, we can say when a force is at right angles or 90 degrees or perpendicular to the displacement of the object, then no work is done. Let's take, for instance, a situation like this where we have an object sliding across a surface. Right? If an object is sliding across the surface, like in this case with this child on the slip and slide, what we can say here is there is no net force or resultant force acting on the object. So what happens if this person is sliding across the surface? It means there is displacement. But just because there is displacement doesn't mean that we have a net force acting on the object. Now, in this case, we would have a constant velocity. Now, if we have a constant velocity, it means that our acceleration is equal to 0 meters per second squared. Now, if the acceleration is 0 meters per second squared, we say that no work is done. Is done as well. So that's another condition. So I can show you how it would look is if I said W is equal to F net delta X. And I said that W is equal to F net, which is MA, multiplied by delta X. And we made the acceleration, let's make all the variables 1, for example. Acceleration is 0. Then you will notice that the work done here is 0 joules. And therefore, work is not done. So that's another condition. All right, so it means that the acceleration must be greater than 0 for work to be done. Now, the standard formula is W is equal to F delta X. You will notice that using this formula in its raw form like this is not usually something that we do, right? Because what you must understand is that because this F over here is a net force, it means we're going to have to do the sum of the forces. And what happens if an object, because what we've been looking at this whole time is this situation. That's the applied force. The applied force is horizontal. What happens when we change the applied force and let's say that's the new applied force? Or there's an applied force that's down there, pushing down. When that happens, we have then got to take into consideration that angle, that theta angle, just like we do when we do Newton's second law. So if we get to the next video, you're going to look at components of work and force and what actually happens if the force actually acts as an angle. How do we make sure that the formula is appropriate for those types of calculations? If you consider it, if I look here, the force that's being applied here, I would say is going southeast. But we know that the displacement here is going to be east. Now the force, the direction of the force and the direction of the object are not the same. So is work being done? Or how can we ensure that in situations like this, we consider those angles? So you'd consider this angle here for theta in order for you to do the calculation to establish whether work is done or not.